Welcome to The Explainer. We click on links dozens, maybe hundreds of times a day, but what's really going on behind the scenes? Today, we're going to demystify what happens in those milliseconds after you click. It's something we take for granted, but the mechanics under the hood are an absolute marvel of engineering.
Okay, so let's just dive right in. You click a link and boom, a web page appears. But what really happens in that split second? Well, your browser sees a name, right? Something like gaia.cs.umass.edu. But to actually connect, it needs a number, an IP address. So the very first thing it has to do is play detective and find that number.
And that's where the internet's global directory service comes in. Think of it like this massive distributed system that's always working tirelessly behind the scenes just to connect that name you typed to the right number.
And that system, it's called the Domain Name System, or DNS for short. It is, quite literally, the internet's phone book. Its whole job is to translate those human-friendly names we can actually remember, like www.example.com, into the strings of numbers, the IP addresses that computers need to find each other. I mean, can you imagine having to memorize numbers for every single website? No way. So whenever your browser needs an address, it makes what's called a DNS query.
Now, this is where it gets really cool how your computer actually finds that address. There are a couple of ways it can ask. The best way, the best practice, is what's called an iterative query. In this scenario, your own local server does all the legwork, asking each server one by one, step by step. The other way is a recursive query, which is kind of like telling another server, hey, you go find this for me and just come back when you have the final answer. The iterative way is way better because it doesn't bog down the main servers of the internet. So this whole process of asking for directions, it's simple, but it's brilliant, and it happens in three main steps. First, your local server pings a root DNS server. Now, the root server doesn't know the exact address, but it knows who to ask next. So it points you to the right top-level domain server, the server for .com or .edu. Okay, step two, you ask that TLD server, and it does the same thing. It points you one step closer to the final authoritative DNS server for that domain. And finally, step three, you ask that authoritative server, and that's the one that holds the actual IP address you've been searching for. It's like a funnel, getting more and more specific. And boom, just like that, the first part of our journey is over. That authoritative server sends back what's called a type A record. That's the official match between the website's name and its IP address. We've got the number. Now it's time to actually make the call. Okay, so with the IP address in hand, your browser knows where to go. But, it can't just barge in. It has to introduce itself properly and then ask for the web page it wants. This is what we call the handshake and the request.
This polite introduction, this is all handled by the Transmission Control Protocol, or TCP. TCP's main job is to set up a totally reliable, ordered, and error-checked connection. You can really think of it like the formal start to a phone call, where both sides say, hello, can you hear me? And make sure the line is clear before they start talking. It's all about making sure the data gets there in one piece.
So once that solid TCP line is open, your browser switches to a different language to actually ask for the web page. And that's the Hypertext Transfer Protocol, or HTTP. It's the specific lingo that browsers and web servers use to chat. You could say TCP builds the road, and HTTP is the car that drives on it. And you know what? The request itself is shockingly simple. It's literally just one line of plain text, just like what you see here. Your browser just sends this little message to the server asking for a specific file. So just remember those two stages. First, TCP builds a reliable connection, and then HTTP uses that connection to ask for what we want. All right, now the way we make these requests has a massive impact on how fast a page loads. And over the years, the protocols have gotten a whole lot smarter about speed. Yeah, the early web protocols, they were not efficient at all. Let's say a web page had some text and maybe 3 images. It would literally have to make 4 completely separate TCP connections, one after the other. I want you to imagine having to hang up and redial the phone for every single sentence you want to say. That is exactly how early HTTP worked, and yeah, it was painfully slow. Let's actually put some numbers on this, using an example from our source material. So first off, just finding the IP address with DNS, that whole 3-step dance we talked about, that takes about 56 milliseconds. Okay, now let's add in the time to actually get the page and those 3 images using that old non-persistent HTTP method. where you have to set up a new connection for everything. The total time just explodes to 216 milliseconds. But with modern, persistent HTTP connections, everything changes. A persistent connection is smart. It keeps the line open after the first request so you don't have to keep redialing for every single image. And just look at the difference. The total time plummets to just 116 milliseconds. That is nearly twice as fast, all from just being smarter about keeping the connection open. And this whole idea of smarter connections, it doesn't just apply to loading web pages. It's huge for how we download large files, too. You've got the traditional way, the client-server model, right? That's where one big server has to send the file to every single person who wants it. But there's a much more collaborative way to do it.
And this is where you can really see the power of teamwork. In a peer-to-peer network, or P2P, the clients, the peers, they don't just download from the server. As soon as they get a piece of the file, they start sharing it with each other. And this chart just says it all. By sharing the load, the total time to get a big 6 gigabyte file is almost cut in half. I mean, this is a huge deal. It's a technology that powers everything from software updates to massive streaming services. It basically turns the entire network of users into one giant server.
All right, so we've found the server, we've downloaded the data super efficiently. But how did the data packets themselves know how to get there? I mean, how did they navigate the huge tangled web of the internet to find that one specific server? How does routing actually work?
Well, the secret is in the IP address itself. It's not just a random string of numbers. It's a unique label that does two really important things. It identifies a specific device, a host, and it also tells you its location on the network. It really is just like a mailing address for your house. And what's really clever is the anatomy of that address. An IP address actually has two parts, and they're separated by something called a subnet mask. You have the network part, which is like the zip code or the neighborhood. It gets you to the general area. And then you have the host part, which is the specific house number on that street. Routers on the internet, they mostly just look at the network part to get the packet to the right neighborhood.
And then, inside a big organization like a university or a company, we take it even one step further. We break up their big network's zip code into even smaller, more manageable neighborhoods called subnets. And we do this for the exact same reasons we use zip codes in the real world. It makes directing traffic way more efficient, it helps with organization, and it can even make things more secure by keeping different parts of the network separate. And the best part? It's all an internal thing. The rest of the internet doesn't even know what's happening. So when you really step back and think about it, this whole incredible journey from translating a name to a number to doing a polite TCP handshake, sending an HTTP request, and then zipping through all these digital neighborhoods, all of that happens every single time you click a link. And it happens in the blink of an eye.
You know, from these DNS lookups to persistent connections and peer-to-peer sharing, the internet is always evolving to get faster and smarter. So now that you know the amazing, intricate journey of just a single click, it really makes you wonder, what does the future of an even faster, more intelligently connected internet look like? That's our explainer for today. Thanks for watching.